Turing, Z3, the first electromechanical computer, ENIAC, the first digital computer, EDVAC, the first digital computer with binary representation, and by the way, also programs stored in there, and combination in 1947, which was invention of transistors. Now, if we fast forward to if we fast forward to today, what we can actually see is that there are three vectors of progress that are coming together. First is that we are continuing to pushing the boundaries of technology of semiconductors. Let's call that, this is the world of bits. Then there are breakthroughs in the world, in the technology of quantum computers. Let's call that, quantums, the qubits. And then there are also really kind of neck-breaking progress that we can experience today in neural networks, and actually artificial intelligence, particularly in the area of neural networks, which are basically these neurons. Now, if I would say in one sentence what is the future of computing, what we expect the future of computing is really this convergence of bits, qubits, and neurons, coming together, proving once again this old Aristotle maxima that the whole is bigger than the sum of its constituent pieces. So let's talk about each of them, one by one, just like we do. Let's start with something that all of us probably know the best, and this is the world of bits. So the bit, canonical, basically representation of the digital world, the values 0 and 1, and the base, the technology base on which particular binary representation is actually done and performed are semiconductors. So that world is what basically is in the foundation of third industrial revolution, fourth industrial revolution, even the fifth one. So there is a tremendous progress in that particular space. And it was, as I said, based and enabled by the technology of semiconductors. Now, in this particular chart, I have these two images. Some of you that are approximately my age will understand the punched cards, right? Because as you know very well, the whole means 1, the absence of whole means 0, and this is how, in the beginning, really in ingenious ways, we were communicating with computers in terms of passing the data or even the program to computers. The second, the image here is a strand of DNAs, and maybe this association is not exactly clear, but what I wanted to drive and associate here with this one is that the latest transistors basically are the smaller than the strand of the DNA. The latest technology of 2 nanometer process that we have, by the way, pioneered in IBM in 2021 is such that each transistor on this chip is actually now just 10 atoms of the silicon. I can't really overstate importance of the semiconductor technology. And as you can see on this particular chart, and please note that y-axis is actually exponential, so this particular line here is not really linear, but it's exponential and fits pretty well with the well-known Moore's law. We can see here that already we are talking about hundreds of billions of transistors on a chip, pushing to almost unbelievable number of trillions. Now we are really coming up to kind of almost subatomic level, and surely these will create some kind of limitations, at least physical limitations in the progress of this one. Why is this density so important? Why we are constantly coming up with them smaller and smaller and more transistors on the chip? Well, for 2 reasons. One of them is really the performance, because, for example, the latest one, 2 nanometers, brought 45% performance improvement over mostly currently used 7 nanometer process. And even more importantly, it's actually less energy in order to operate them. So again, if you compare 2 with 7 nanometer process, we see that of 75% performance improvement. Now, obviously, we can't just continue like this all the time because, as I said, we are already at atomic, subatomic level. But we still have some tricks up our sleeves how to do that, how to progress in semiconductor world. Some of these I would like to share with you today. There are different methods that are basically used, but some of them that in our research, in IBM research, we basically look at a lot, is so-called memory on-chip technology. And this particular one here, called North Pole, is something that we are currently exploring and developing. And I believe that in the future we will see more about this. Now, what is this all about? You see, from the very beginning, when we started with semiconductor, when we started with digital computers, the technology to deliver processors versus memory was actually different. Different in terms of the characteristics for executing, but also in terms of the price. So that kind of separation of processing and memory, as you know very well, even today, has become very pervasive and delivered actually very, very good results. But we are pushing already some, particularly in some areas, like inferencing of actually large language models or in general foundation models. We are coming to the situation when the current von Neumann architecture, where the processors and memories are actually separated, are hitting some limits. And these limits manifest themselves with, I would say, unnecessarily large energy consumption that we need in order to process some processing patterns. And as I said, foundational model inferencing is exactly something like that. So what we are coming up with are the architectures where the memory is actually on the chip itself. Now, this particular chart here shows you different architectures, like, for example, GPU, which you know very well, is really the workhorse of the inferencing and modeling of large language models. You can see it here. This blue little thing here is actually the amount of memory on the chip. With GPUs, with tensor processing units, like Google's ones, with the CPU, this particular one is, for example, AMD, you see that on the chip, what you have memory is relatively small. What we have, the architectures with memory on the chip, like you'll see on your right-hand side, which is this North Pole, has a larger piece of memory within the processor. And that way, we are basically minimizing the transfer of data between processor and memory. And we have found out that for neural networks, particularly for inferencing part, we can come up with factors faster processing, basically reducing latency, which is important, but also coming up with a much better energy consumption of these processors. So this is something that you might want to, that you will probably see in the future coming up as the way to address the energy consumption and the latency of the inferencing systems. Good. So that's about that one, right? Let me then introduce these two additional vectors that I said. One of them, qubits, another one, neurons. But let me do that in a kind of, for me at least, an interesting way of talking about data representation. And as you know very well, it's a common approach, scientific approach, where you take a problem that originates in one particular space, and then you transform it into a different space. In that process, you basically unlock some of the characteristics that you were not able to see in the original space. One of those is something that you all know, like, for example, if you take electrocardiogram, right, which is basically a signal, and you transform it via Fourier transformation into the spectral representation, doctors can basically see, for example, some anomalies in a heart functions that you wouldn't be able really to hear or detect if you were just listening heart. So this particular notion is all over the place. And in IT, I want to draw your attention to two particular ones that happen. For example, one is with relational representation. When the industry came up with the idea of to represent the data in a basically two-dimensional array, what happened is that is underpinning, hundreds of billions of dollars industry that IBM and Oracle and Microsoft and many other companies actually benefited from. The next one is graph representation. So when we came up with a way to represent the data and the relations between data and the graph, we came up with companies like Facebook, like Google, like LinkedIn, like many others actually came up and figured out. Sorry? Financial industry and so on and so on. So basically, right. So basically you can see it's interesting to think about that data representation, new way of representing data suddenly opens up almost a new industry. And what we believe now is that these two new data representations, one of them in neural networks, another one in quantum circuit representation, is actually has the same capacity, like, for example, relational database or graphic databases. Okay? So let's talk about, for example, first of the qubits and the quantum computers. Now, as I said, binary representation of data and bits and semiconductors as underlying platform have been underpinning basically everything we do, okay, in the last 40, 50, 60 years, like maybe 80 years in this industry. But nature itself is not really binary, okay? So what we do with the binary representation, we are simulating the nature. And we are doing that extremely, by the way, well. However, there is a class of problems that simply by simulating by the binary representation and using the semiconductors to fix it is not going to work. And we know that. Take, for example, take the auto industry, okay? And you know that every large auto manufacturer has this wind tunnel, right? Because now we are talking about dynamics of fluids. It's a complicated natural phenomenon, which is not really easy to simulate. Because if it is easy to simulate, there would be already very good simulation software programs that will be used in order to figure out the aerodynamics of the cars. By the way, it doesn't mean that they don't exist, but still, every major auto manufacturer, and I know that very well because I live in the middle of those back in Germany, has a wind tunnel where basically this dynamics is simulated, emulated rather, and then the results used in construction of the cars. You see, this is a very good example where the basically binary representation or like simple software program is not going to really deliver what is needed. Maybe it could, but it requires lots of resources. Lots of resources. Like, for example, everybody knows now that for encryption today, whether this is encryption of data at rest or on the wire or something like that, we are using EAS or some of the algorithms, most of them basically based on a premise that is really very hard to figure out what are the prime numbers making up an arbitrary integer. Again, classical computers can theoretically actually break this down. It can figure it out, but it requires maybe hundreds of thousands of years in order to do that. Now we are coming up to the qubits. We are coming up to quantum mechanics, which is really like, look, by many means, is actually emulating nature better. And if we manage to come up with a computer which doesn't have just the values of 1 and 0 in order to encode the data, but 1 and 0 and 1 and 0 at the same time, and everything between 1 and 0 all the same at the same time, this is something that basically can enable us to capture and resolve all these exponential non-polynomial problems that are really difficult for the binary computers and classical computers. And that's exactly what quantum computers actually bringing up. I would like to say that quantum computing is also not a panacea that is going to now suddenly replace our classical semiconductor and classical computer. We should rather think about that as something which complements it. So take an example I read somewhere a nice kind of comparison with that one. If you want to get somewhere, you usually take a car and get to the airport, and then you fly, and when you land, you take a car and you get somewhere, okay? Well, this is kind of what we believe is something which is similar to happen. We are going to use a classical computer to basically get the problem, to understand, to orchestrate it, to understand what needs to be done, and then call quantum computer for the pieces of the processing for which classical computers are not really well suited. Then when that is actually done, classical computer is again going to get the control to get back the result back to you. Okay? So it is going to be the hybrid, and that's exactly how our systems currently, IBM systems, that are available for anybody actually to try, and this is what I would really like you to take with you today. We do have a systems already today, not in press, but actually in reality, in which you can log on and work and use Qiskit and use quantum computers and programs and to test and see how that actually works. So that's exactly how these systems work. Okay. Now, the quantum computers are based on quantum mechanics and on the phenomena from a quantum mechanics like superposition, entanglement, interference, and everything else. And of course, I'm not going to try to explain these phenomena. I also want to tell you that for most people, including very, very technical people, and even academically technical people, these concepts are at least, how would I say, not really intuitive, okay? Because it's not easy really to intuitively understand why something can be and not be at the same time. But my point here is that we don't really necessarily need to understand how that works at the basic level. I would argue that out of tens of millions of software developers in the world, okay, maybe 10 million, 100 million, I don't know how many of them, I would argue that a huge majority do not really fully understand how, on the physical level, semiconductors work. I apologize if I offended somebody. You know that, sorry about that. But the folks that I talk to and so on usually do not know exactly how that works at that level. Okay? And that doesn't really prevent them at all to build absolutely phenomenal solutions, software solutions and program and everything else, right? Same thing I would say with the quantum computing. There's really no need for us to understand superposition and entanglement and interference and all these crazy things that is really difficult to understand, to fake them, in order to use it. So my suggestion is, get on the board right now and start using this stuff. Get prepared for something that will, we believe, very, very soon actually come. Okay. There are folks that, for example, say, very important by the way, from different companies that are also building with the quantum, doing with quantum computers and so on, and say that it's not really ready for the prime time. Okay. The reasons why it's not ready for the prime time, because we are still trying to figure out answers to some difficult questions, okay? And these difficult questions are, for example, qubit stability. Qubits are not really stable. So, for example, in our particular implementation of quantum computer, it needs to be at in the cryogenic units with almost 0 Kelvin, and so that's one thing. Another one is that the error correction in a quantum computers is still not fully figured out. But you know what? This is the reason why I put this here. Let's learn from a history where classical semiconductor-based computers were invented and worked. You see, they actually were used all the way from 37 to 45, and only in 50 we actually had a Hamming error correction that allows us, even today, to use these systems reliably. So, quantum computers, as of today, if you take it, is not as reliable as a classical computer, but it doesn't mean that you shouldn't be really already using it, taking this into account, and figuring out what are the use cases that quantum computer can actually help you execute much better than a classical computer. So there is no need to wait, because the error correction codes will come, okay? And then you will have a competitive advantage because you are already in that space. Good. Now, if you ask where quantum computers are already kind of being used, experimented with, played with, and so on, I can tell you that out of all the quantum computer centers that we have around the world, some of them very large, with many 150 qubit systems and so on, these are basically the typical areas of the companies that are using quantum computers. They are in simulating space, they are in, of course, complex mathematics, and then search optimization. And then mostly what I can see is, for example, material science in figuring out the batteries for electric cars, okay? Extending the life of that, or high-speed trading, and so on and so on. So, as I said, many companies and research organizations are already doing this. So this is something not to, I would say, wait and see what's going to happen. In terms of what IBM offers in the quantum computers, you can see here there are lots of computers with more than 100 plus qubits, which, by the way, allow you to do lots of cool stuff already, with a very large ecosystem of the researchers and companies and developers and so on to actually use the system. Okay? As a matter of fact, in my lab in Germany, southern Germany, we just got installed one 150 plus qubit system, which is available for public use. Okay? So I want you to take this with me, okay? With yourself. They are already available for you to use. So it's not a theory that is somebody making publicity about that one. They're actually already available for you to play and use. Okay, let's talk about the last one, okay? Which are neurons, which are basically artificial intelligence, particularly the large neural networks in artificial intelligence. Because as you know, large neural networks is not the only thing about artificial intelligence. In this industry, the AI had, in the past, created lots of attention, lots of hype, lots of expectations, and then after a few years or shortly after that, just died down. So this is called AI winters that are, by the way, known, that existed for quite some time. So I would say a reasonable question is, are we expecting AI winter again after all the hype and everything else what has happened?
Yes.
For example, I have already read some of the articles in a serious magazine, some serious, I would say, industry analysts are saying, well, this is already overhyped and so on and so on. And I would argue, and we in IBM it's not. There is not going to be AI winter this time. And I'll tell you why. Because there's something common for the previous AI winters. Number one, there were not enough processing capacity for actually executing these very intensive processes that neural networks require. And today, we have multi-scalers with a tremendous amount of resources, including, of course, tremendous amount of GPUs, which, by the way, I would say, hey, what? I don't know. because GPUs were not really built for inferencing and building large language models. As you know, GPUs are built for, as the name says, graphical processing units for rendering two-dimensional screen. That doesn't matter. It fits perfectly, really, for the neural network operations. So we have that. The next thing that we didn't have before is something that AI and large networks absolutely require, which is lots of data. And now, through internet and all the availability of the data that is constantly growing, we have that. Okay, that's the second one. And I would say there's a third one, which usually people kind of somehow ignore, but I believe it's one of the most important. Previous algorithms, in most cases, I'm talking about AI algorithms, I'm talking about neural networks, right? They have, sorry, I have to fix this one. Coming from, okay? They were supervised algorithms, okay? That meant that you actually had to, like the data scientists or data engineers or whatever, label data, classify data somehow, tell what this data means in order for algorithms to actually build the models. But that doesn't scale. That doesn't scale because if you have lots of data, it really takes lots of time to classify, to label the data. Of course, what we have tried to do that, how we try to tackle that problem, we have built software solutions that were labeling data and so on. But all that didn't really work well. And that was another reason why we had AI filters. So I'm saying also the algorithms that were used were not appropriate. But with the new family of algorithms, with non-supervised building models, we don't need to do that. And all of these that we see here that are building on the large language models are exactly like that. So that's a third reason why I believe there is not going to be AI filter. And this is something which is important to take into account. Okay. AI is all over the place. I don't have to convince you about that one. This company that I work with is in this business for 114 years, okay? And we can surely say that we have either created or co-created or witnessed to creation of everything relevant in IT, okay? And still, we believe that this thing, AI, has probably the largest potential to transform the way how we actually live, to transform the way how businesses work. And from that perspective, it is very, very attractive and exciting. It reminds me on how the mechanical machines have augmented basically human physical capabilities in the first industrial revolution. And I'm using this augmented to kind of convey the message that A in AI doesn't necessarily need to mean artificial intelligence, but it might mean actually, it should mean augmented intelligence. So similarly to these, the machines, mechanical machines augmenting physical capabilities, AI probably, and we hope, will augment mental capabilities, intellectual capabilities of the human. So, as I said, we expect huge things out of that one. And I don't also have to probably convince you about how eye-opening and how fantastic some of these results of AI even today are. But for me, this particular chart actually tells this better than anything else. This is the chart that shows you how quickly the AI benchmarks saturate. Okay? So, at 100% here, you have a performance of a human. And this is basically the reference point. So the benchmark is made in such a way, like for example, image classification or reading comprehension and so on, in such a way that how the system performs compared to a human. And you can see that the more we go along the timeline, these benchmarks actually reach capabilities of a human ever faster. So last year, 2023, I checked, and for example, the competition level math, this light blue line, was still below human performance. Okay? And now, just a couple of weeks ago, I read something that was really phenomenal. In Carnegie Mellon, I believe that one of the speakers was actually from Carnegie Mellon today. There's a professor of mathematics, and he created 10 exercises. And these are the 10 exercises basically for the students and that compete in mathematical Olympia. Okay? So these are very tough things. And OpenAI O1 model solves each of these problems in 1 minute. Okay? So it's already better and faster than what human can do, even on these competition level mathematics. Okay? Good. We at IBM, in addition to building some of the models, but we actually much more engaged in building the solutions with our businesses that work with us, with our customers. And here on this particular chart, you can see lots of these examples. On the next chart, you can see the footnotes and links. And by the way, I have made this presentation available in a PDF format to our local IBM colleagues. So if you want to have that and you want to know more about details about all these kind of benchmarks, and by the way, any other charts, you can reach out to them. But you can see here that in most cases, in red, I have actually marked those that are most common. So in most common cases, when we work with our customers, these are the AI solutions in the HR area, customer service, and particularly in the IT development operations. So application modernization, of course, IT automation, AI ops, and everything else. Okay? I guess it won't surprise you, but that's exactly where we see our most engagement, most action when it comes to the AI. So this presentation would be okay if I wouldn't mention, of course, AI agents, absolutely the latest thing that are coming up. I believe very, very, very exciting. And in my opinion, this is a very good material for building killer apps, apps that really makes difference in the business. What is the today killer app for AI?
Chatbot.
Sorry?
Chatbot.
Chatbot. Okay, not bad. But let me tell you what I mean under killer app. Back in 90s, late 90s, when internet came up, okay, everybody was talking about internet. I remember that very well. Exciting, there was a huge excitement. Wow, that's going to completely transform industry and everything else and so on. And it was true. And I feel that these times are kind of similar to that. Technology has come up, which with huge capacity and potential. And we all talk about that, and starting with me, I also believe in that. But back in the 90s, there was no really killer app. There was some kind of digital transformation ideas and everything else. The real killer app came in 2007. That's iPhone. So this is what I think killer app. Okay? And if we compare, for example, chatbots with iPhone, I wouldn't say it, right?
I think Google search was a killer app. 94.
Google search, but this is Google search is also a killer app for internet, right? Which also came much, much later.
Much later, 94, 95. Yeah,
but not in this sense that it came like that. So what I'm saying is that in that level of a killer app, I believe that we are still waiting for this kind of thing. Sorry?
iPhone gave a disruption for all the models, like BlackBerry. People used to receive an email from Office, but then iPhone started initially, and then came on the WhatsApp, and then every day new apps and apps.
I can think also about the innovations that basically disrupted industry. I mean, Uber, Airbnb, Amazon. I mean, these are the phenomenal killer apps that are basically built on the internet. Okay, so I expect, my message here to you is the following: I expect that AI has that capacity what internet had. Okay, and that these killer apps are still coming. Okay, still coming. So it's all up to all us here to come up with 1, 2, 3, and so on. And agentic AI appears to me yet another step into that direction. So it's definitely something that makes sense to explore, makes sense to have an eye on, makes sense to start building on, and everything else. I won't explain what that is. I heard in these 2 days many times people explaining that and so on. But that's basically something which I believe that has a huge potential for going forward. Okay. From all these engagements that we have, and literally we have hundreds, if not thousands of engagements with our customers building AI solutions, we have come up with these 4 principles that we believe that if we are, for example, building a Gen I application, that large language models are underpinning that would need to have. And these are what I mentioned yesterday in the panel. These are open, trusted, targeted, and empowering. Okay? First of all, quickly just about open. We believe that large language models should be open without buts, ifs, and so on. Okay? Simply open with the most permissive Apache 2.0 license. Because if they are open, then you are avoiding being locked in any kind of proprietary solution. And most importantly, I believe from a technology perspective, you give opportunity much larger community in order to build up the model, to contribute and work on something rather than just a single company. And when I talk about open models, I will not have time really to go through that. But you can see here how the models are being delivered throughout the years. These are kind of notable models. And many of them are called open. But not really many of them are really unrestricted open. Unrestricted open, as I said, with this license, which is like an Apache 2.0 license. So again, there is a link here in the PDF file that you can get if you want. So you can go in there and read more about this. But OpenAI, for example, there's OpenAI, ChatGPT, GPT. This is API. This is not open at all. Okay, it says OpenAI. It's not open at all. Okay, but no, it's API access. Some of them, even DeepSeek, which is open. Yes, it is open, but with restricted use. You can't redistribute it. You can't use it in every sense. The weights are not exactly clear, and so on and so on. So anyway, have a look at this one. My message here is that I believe the right way in order to choose the right model, it should be open. Next one is targeted. And the targeted, what I mean is that these large models that are built on hundreds of billions of parameters have a carbon footprint. They cost a lot to build. They cost even more to run, because according to World Trade Organization, 20% or actually of the power goes to building a model and 80% on actually running it, like inferencing the model. So smaller models which are targeted for a particular use case is something which we believe is much more appropriate. These models are also easier to handle